In this video, I will go over the dynamic programming algorithm to compute the edit distance between two strings. In this problem, we are given two strings A of length n and B of length n, and we want to compute the minimum number of edits to transform A into B. And when I talk about edits, we can think of three operations. We can insert a character into A, or we can delete an element from A, or we can substitute a character in A with another character. There are several applications to this problem, but we can think of computing the edit distance as a way to measure the dissimilarity between two documents or two DNA sequences and so on. So if you have two documents, you can use the edit distance to check how close or how dissimilar they are from each other. Alright, so how do we go about solving this problem? So let's consider a concrete example. Say A is the string snowy and B is, and consider B as the string sunny, and we want to know at least how many edits, including insertions, deletions, and substitutions that we need to apply to A so that we can transform A into B. We can think of this process as placing gaps into A and B and align them together. What do I mean by this? Let's look at an example. For example, we can place a gap at the beginning of A. And place another gap between the letter W and the letter Y. Okay. And in B, we might place two gaps between the two letters N. Okay. So if we place the gaps so that they have the same length and we align these two strings together, you can think of this as a transformation as follows. The first columns correspond to an insertion. Basically, this means that we insert S into at the beginning of A. Okay, so if we have a letter at the bottom and a gap on top, that corresponds to an insertion. Now, if we have a gap at the bottom and a letter on top, right, that means that corresponds to a deletion. Similarly, the second last column corresponds to an insertion. Now, for all the columns, if we have two letters that are not similar, like the second column, then that corresponds to a substitution. Okay, so we can think of this process as the following. So we start with snowy. Okay, now we inserting S at the beginning. Okay, and then we substitute the second S with a letter U. Okay, and then we delete the letter O. And then we delete the letter N. I'm sorry, the letter W. And then we insert a letter N between the letters N and Y. So this corresponds to a transformation with how many edits? 1, 2, 3, 4, and 5. So the number of edits in this transformation is 5. But this is not the optimal way to transform A into B. For example, we can do something like this. We place a gap between two letters S and N. In A. and we place a gap between the last two letters N and Y in B. Now, in this transformation, we only have an insertion, a substitution, and a deletion. So you can check that the number of edits here is 3, right? So you can visualize it as the following. So you have Snowy, that's what we start with. So we insert a letter U between S and N. And then we substitute the letter O with the letter N. And then we delete the letter W. So this gives us indeed a better way to transform A into B with fewer number of edits. It turns out that this transformation is optimal. So the goal is to figure out what is the best way to place the gaps into these two strings and align them together. Now we will use dynamic programming to solve this problem. We need to appropriately define the subproblems. So I will define the following. Let EDIJ be the edit distance between the prefix A1 up to AI and the prefix B1 up to BJ. Alright, so let's look for the recursive structure. To transform the prefix A1 to AI into the prefix B1 to BJ, we consider the optimal transformation or the gap placement. Now, if you look into the optimal gap placement, there are 3 cases. For the last column. So the first case is the following. We have the letter AI on top and a gap at the bottom. So this corresponds to first we transform A1 up to A minus 1 to B1 up to Bj, and then delete AI. So the number of edits in this case would be 1 for the deletion plus the minimum number of edits to transform A1 to AI minus 1 to B1 up to Bj. So that would be the edit distance between these two strings. So that would be ed of I minus 1 and j. Alright, so that's the first case. Now let's go into the second case. Again, in this case we have the letter Bj at the bottom and a gap on top. So this corresponds to transforming A1 up to AI to B1 up to Bj minus 1, and then insert Bj at the end. Okay. The number of edits in this case is 1 for the insertion plus the edit distance between A1 up to AI and B1 up to J minus 1. Finally, we have the last case. That is, you can pause for a moment to think about it, but in this case we will have AI on top and Bj at the bottom. So this corresponds, okay, so if AI is equal to Bj, this corresponds to transforming A1 up to AI minus 1 into B1 up to Bj minus 1, and we are done. So if AI is not equal to Bj, then this corresponds to, first we transform A1 to A1 to AI minus 1 into B1 up to Bj minus 1, and then substitute AI with Bj. Okay, now what is the cost of this case? Okay, so let's diff ij to be, let diff ij be 1 if AI is different from Bj and 0 otherwise. So in this case, the number of edits is equal to the edit distance of the prefix A1 up to AI minus 1 and the prefix B1 up to Bj minus 1 plus diff of I and j. So we are done with the 3 cases. Now we have the following recurrences. Because we don't know, which of these is the optimal way to transform one prefix to the other, but we know the optimal transformation must be one of the following 3 cases. So we take the minimum of the 3. So okay, so that's the recurrence. We still need to address the base case. So it turns out that the base cases for this problem is fairly simple. We simply consider ED of 0 j to be j. This is because to transform an empty string to a string of length j, the only way you can do it is to just inserting j letters in the other strings. Similarly, the edit distance of I and 0 is just I. So to transform the string of length, the prefix of length I of A into an empty string, the only thing you can do is to delete I letters from that string. Okay, so this is the base case. Okay, now let's complete the algorithm. We simply have a for loop for I and a for loop for j. And we just, copy this recurrence down. And finally, we simply return ed and m, which is the edit distance between the whole string A and the whole string B. It is fairly easy to see that this algorithm runs in n times n times n. And based on some complexity assumption, this is the best running time possible to compute the exact edit distance. So I hope you learned something from this video. Hopefully you find it useful, and I will continue this series in another video. Thank you. Goodbye.